Hi everyone. In the last video, we saw how to compute the inverse of a 2 by 2 matrix using just a formula that was pretty syntactical. In this video, I want to show you how to compute the inverse of an n by n matrix that works for any size matrix. But let me just point out that we're talking about an n by n matrix. That means that inherent in everything we're going to do, we have to have a square matrix. First, I want to run through a little bit of just explanation about why what we're going to see works. Our idea is to find a matrix A inverse so that A times A inverse will be equal to the identity matrix. Now, we are working now in the context very much of systems of linear equations, and we have seen now that we can write a linear system like this, right, as a matrix equation. And when we set up an augmented matrix to solve a linear system, what we're building is something that has this matrix A, and then we usually put a bar and then the B vector stacked up on the right side of that bar. And then we perform Gauss-Jordan elimination, right? So we transform A into A1, we transform B into, I'll call it B1, and to do that we use an elementary row operation that we know we can represent with an elementary matrix. And then we do it again, and again, and again, as many times as we need to until we get to the end, which hopefully, if we have a unique solution to our linear system, looks like this. Right? It's got the identity matrix on the left-hand side of the bar, and then on the right-hand side we have a solution vector. And we know also that when we represent these row operations as elementary matrices, the idea with that is that we could get from A to A1, for example, by multiplying the A matrix by E1. So if we start with A and multiply by E1, that's A1, and we multiply by E2, that'll give us A2, and so on until we get to the last one, EK, and we multiply that by everything that we've done before, and that will give us the identity matrix. So since we are after something that will give us an A times A inverse equals I, and in the case of inverses, this is actually true for multiplication on either side, then what we've got here is our inverse that is sitting in the product, represented as a product of these matrices. So this is A inverse. Next, let's see how to find A inverse by executing this algorithm and keeping track of the row operations. So here's an example of a matrix, and I'm just taking a coefficient matrix now and ignoring the B vector. And what I've done here is I've started with this matrix and proceeded to go through these row operations to get this a row equivalent reduced echelon form matrix. And it looks just like the identity matrix. It's a 3 by 3 identity matrix. And at each stage, when I've done one of these row operations, there's an elementary matrix that I can write down that will encode that row operation. So in this case, E1 would be the matrix that takes the difference between row 2 and row 1 and puts it into row 2. And E2 is the matrix that scales row 1 and row 2 by a half and a third. And finally, E3 is this matrix that subtracts 2 times row 3 from row 1 and adds 3 times row 3 to row 2. Okay, so these are our 3 elementary matrices, and from the idea we were talking about before, I can think of this, this process of going through this elimination method and getting to the final result this way. So I start off with matrix A, I multiply it by E1, and then multiply it by E2, and then multiply it by E3, and then I finally get to the identity matrix. So this is A inverse. All that remains now is to actually compute it, and we can use what we know about elementary matrices to make this computation easier than it has any right to be. I'll start by multiplying these two, so I'm just going to copy this first one down again. Now when we want to write down the product of these two matrices, Remember that what we're doing is multiplying a matrix on the left by an elementary matrix, and we know what this matrix does. It scales the first row of the other matrix by a third and the second row by a half. So I don't need to do any of this working across the columns and the rows because I know what this does. I know that this matrix is going to be 1/3, 0, 0, minus 1/2, 1/2, 0, and 0, 0, 1. And I also know what this matrix does. This matrix, this elementary matrix on the left, is going to take this row and subtract 2 times this third row. So I can write down right away again what this matrix is. And for the second row, this matrix says take the second row and add to it 3 times the third row. So this now is our A inverse. To check to see if we got the right answer, we can just take the product of A with this A inverse that we just found. So let's scroll up and do that. Okay, so here we've got our A and our A inverse. So now we can just multiply these two together to check to see if we've got the identity matrix. So 3 times a third plus 0 plus 0. 3 times a third is 1. And then we'll have 0 times 3 plus 0 plus 0. Minus 6 plus 0 plus 6. And so on, right? You can work through this. Here's 1 minus 1. So maybe pause the video and work through it yourself. We get the identity matrix as our check, so this matrix is indeed the inverse. Now I want to show you a shortcut of sorts to allow you to compute the inverse of a matrix. And I think I'll just keep using this same example so that we can see how it's working. Okay, I've just copied some of the work from our previous page so that we can reference it when we're doing our next work to see how this shortcut works. So here's the idea. When we multiply these 3 elementary matrices together, you can think of them as like acting on the identity matrix. So if we took the identity matrix and we did this to it, we would get this. And then if we take the result of that and do this to it, we'll get this. And if we take this matrix and do this to it, we'll get A inverse. So why not just do all those things along the way while we're doing that row reduction? It saves us having to multiply all that stuff together at the end. Let me show you what I mean. The way that we're going to do this is we're going to set up something that looks kind of like an augmented matrix that has our A matrix on the left-hand side of this bar, and then instead of just having a B vector, we're going to have an entire copy of the identity matrix on the right-hand side of the bar. And then when we perform our row operations to get the left-hand side into reduced echelon form, we'll be doing those same operations on the identity matrix and keeping track of everything as we go along. So recall here, we're going to take row 2 and subtract row 1 as our first step. So now all the way through, I'm going to do row 2 minus row 1. First row stays the same though. So row 2 minus row 1 is going to give us 0, 2, and negative 6. Row 2 minus row 1. So we'll have negative 1, 1, and 0. And then the last row stays the same. Then we're going to do this scaling. Okay, so let me pause and point out that this matrix looks just like E1. Now if we take care of this scaling operation, let's see, we'll get 1, 0, 2, 0, 1, negative 3, and 0, 0, 1. I'm going to do the same operations to the right-hand side. So we'll have 1/3, minus 1/2, 1/2, 0. And so now just let's pause a second and notice that from our previous calculations, we can see that this is the same as E2 times E1, right, which is what that matrix was. Now let's clear that third column with the backwards elimination. So I'll use these row operations, and when I run through them, I'll get 1, 0, 0. This is row 1 minus 2 times row 2. So I'll have 1/3 minus 2 times 0, 0 minus 2 times 0, and 0 minus 2 times 1. In the second row, I'm doing row 2 plus 3 times row 3. So 0 plus 3 times 0, 1 plus 3 times 0, negative 3 plus 3 times 0 is 0. Negative 1/2 plus 3 times 0 is negative 1/2. 1/2 plus 3 times 0 is 1/2. And 0 plus 3 times 1 is 3. And finally, the last row in this case stays the same. Now, on the right-hand side, we have E3 times E2 times E1, which is equal to A inverse. So that's the strategy and execution of how we're going to find the inverse of a square matrix. This is the way it's always going to work. We're going to set up the matrix on the left-hand side of a bar, and then the entire identity matrix of the corresponding size on the right-hand side, and just do the same work we would always do to get this matrix on the left-hand side into reduced echelon form. And then whatever we end up with on the right-hand side is going to be our inverse. In a later video, we'll talk about the computational cost of this process in terms of the time complexity.